Hello guys, in this video we are going to study about capnography, which is a topic from anesthesiology, and a lot of questions are asked from it. Right, so here you can see this is a photo or a graph of the capnography, which we can see in an anesthesia machine, and we have to know about it. The normal capnography graph starts from the 0 point, right? 0 here means 0 is millimeter of mercury of CO2 that is expired that we get from the endotracheal tube, right? Means this amount of CO2 which the patient expires. So expiration starts from this point, but still CO2 is 0 in this phase. Why? Because of the dead space. In dead space there is no ventilation, and that's why oxygen comes and CO2 doesn't come. After the dead space is over, there is a rise in the CO2, and the normal EtCO2 maximum is between 35 to 45. Then there is a plateau and then decreases because of inspiration, right? So this is a normal EtCO2 graph. It looks like this. Now we have to study about the abnormal patterns. You can see over here there is a dip in the EtCO2 graph in the plateau phase, where you can see over a dip. This dip is known as the curare cleft, right? This is known as the curare cleft. It is a very important photo, has been asked in INICET and NEETPG. And where do you see this type of graph for the curare cleft? It is seen in case of return of spontaneous ventilation, right? Return of spontaneous ventilation. When the patient is in anesthesia, we give neuromuscular blockers, and when we give neuromuscular blockers, the neuromuscular blockers effect fade away. Then if the effect is faded away, then we can see this type of graph, means curare cleft can be seen. So it is seen when the patient puts his own effort for ventilation, right? So this is called return of spontaneous ventilation. So what is the treatment if we see that this type of graph is seen and the patient is under anesthesia and OT is going on? We have to give another dose of the neuromuscular blocker, just for example atracurium or succinylcholine, whatever we have given. Second graph is this. You can see over in the graph that this graph is not starting from 0. This graph is starting from, for example, plus 10 and is going to, for example, 40 to 50, whatever it is. Right, so there is a rise from the basal level of EtCO2. EtCO2 is never going down to 0. And where do we see it? In case of rebreathing. In case of rebreathing, the patient again inspires a few amount of CO2 which the patient has expired. Because the anesthesia machine is a closed system, that's why the CO2 which is expired by the patient is absorbed by the soda lime, right? So we absorb the soda lime in the ventilator machine. If in case of the soda lime is exhausted, then we see such type of graph which is called rebreathing. Next graph is shark fin pattern. This is called shark fin pattern because it looks like a shark fin right above the sea level. Where do we see it? Very important, bronchospasm. Bronchospasm means partial obstruction of the airway, partial obstruction. If the obstruction is full, then the graph would be a straight line, right? Next, coming to the fourth graph, this occurs when we do esophageal intubation. This type of graph is seen in esophageal intubation. This is normal ventilation curve. Normal ventilation means when the patient is breathing by his or own, right? And the ventilator machine is not giving the breaths. This is cardiac oscillation. This is seen when there is cardiac oscillation. Next is, there is a graph, as you can see that the first graph, the EtCO2 maximum is 35, then the next is 50 and another is 70. So it's keep on increasing. So where do we see it? We see it in malignant hyperthermia, right? Malignant hyperthermia. And the last graph, we can see that all the graphs don't look very particular like the EtCO2 graph, and there are EtCO2 is variable. We see it in CPR.